In this video, we want to solve two transportation problems. Since we can write the linear programming model for any transportation problem, here we try to solve these problems by simplex method. But simplex method is not the most efficient method for this. We can solve it for sure, but there are other methods, especially if the number of sources and also destinations are large numbers, and we have, for example, if we have m rows and n columns, then m times n is going to be the number of decision variables, and also we are going to have many constraints, so it's not going to be a good idea to solve with simplex method. So here we just solve by simplex method to show that we can find the solution for this problem, and also we say that this is not the best way. We will study two other different methods which are efficient methods for this type of problems. One of them is going to be based on network or graph. We are going to consider the problem as a network. On the vertices we have sources and destinations. For the sources we are going to use positive numbers, for destinations, or we call them sinks, also negative numbers, and it shows that we need something in this destination since it's negative. And for the sources we have positive, we have this much of products to send to the destinations. For the sources we also say that we have this many products to supply. And for the destinations we say that there are these demands in the destinations. So usually we show this blue part of this row and column, we call them SIs and DJs to show that these are the supplies and those are the demands. So these information are given in the problem. We will read the problem and extract this information. The yellow part is something that we call dummy or imaginary. We need it if the problem is unbalanced, and I will show you how we determine whether the problem is balanced or unbalanced. So these are the terminology that we need to know when a problem is balanced, or how we can change or convert unbalanced problem to a balanced problem by adding a dummy source or dummy destination. But we need only one of them. In case the sum of supplies that I wrote here, as you can see, this is the sum for this column, the sum of SIs, or here this number is the sum for this row, the blue part. The yellow one is something that we need to add later on if the problem is unbalanced, so I don't add that one here. Since this total supply is more than total demand, we say the problem is unbalanced. But here I wrote some rules. I will show you how to write them. Especially in the second exercise, it's better to see there, because there I have dummy row and column at the same place. If we need, we are going to use. Otherwise, we can leave them there and we solve our problem without dummy row or dummy column. And also here I wrote a conditional statement. If these are not the same, then we are going to write the problem. If they are the same, we write the problem balanced, otherwise unbalanced. And also you can see that the color code also is there to show that the problem is balanced or not without looking at the numbers. For example, since we have 150 and 100, so supply is more. If I subtract something from one of the supplies, for example, if I change this one to 0, then it becomes a balanced problem, and the color also changes since I put a conditional formatting to that cell also. So for now we have unbalanced problem, and in case that the problem is unbalanced, we need a dummy or imaginary row or column. When the supply is more than demand, here I wrote supply more than demand, we need dummy demand. And the DJ for that, this number, is going to be the difference between these two. So here you can see also I wrote a rule. This number is this sum, this 150 total sum for supply minus total sum for demand. Another thing that we need to know here, these numbers here in the gray part are called cost coefficients, CIJs. For example, this 50 here means If you want to send 1 unit, so 1 unit can have different meaning. For example, in this exercise, we will see that by 1 unit, we mean 1 ton of the product, okay? So for 1 unit of commodity, here also, for example, we have 50 tons to be supplied. So for 1 unit of commodity or this product to send from source B to destination Q, we need to pay C to 3. So since this is second row, this is third column, so I refers to the row number, J to the columns number. When I write C23, it means that the cost for sending 1 unit of commodity from source I to destination J. And also we want to decide about that. We want to decide how much to be sent from source I to destination J. So Xij are going to be our decision variables. And based on this, Cij is exactly the same number of variables will be Xij's for us. And if we need a dummy column or dummy row, then the number of variables will increase like this. Right now we have 3 times 4, 12 decision variables. How many constraints? Since adding this column, the problem becomes balanced. If I want to send the products, all of them sent out, then all the demands will be satisfied. Or if we want all the demands to be satisfied, we need to send out all the sources from A, B, C. So then all the constraints are going to be equality, and I will show you how to write the constraints. So for now, this is a given problem. It says that this 30, 40, 10 are cost coefficients to send 1 unit of commodity from source A to destinations M, N, Q, and so on. And also, the unit also is given by this 30, it means $30 per ton. So, and also here we can see that it says for the supplies, they have the same size and the capacity for them are 50 tons. So these 50s here are coming from this sentence here. But for the demands, we can see that here for the customers or the MNQ, these centers, we need to send this many units, 30, 45 and 25. So this 30, 45, 25 comes from here. If the sum of these elements are the same in the row and column, then the problem is balanced. You don't need this yellow column or row. But in this case, we see that it's unbalanced and we added this. And the number here is going to be the difference between these values. So this is how to create this tableau here. This is the original part of the problem. Now, first of all, we want to solve the problem, find the optimum solution. It means that what's going to be the minimum cost to send out all these products and provide all the demands like 30, 45 and 25 here. The blue parts are important for us. In the yellow column, we can see the zeros here. Since it's imaginary, we are not going to send to that. This is just there to make the problem balanced and to be able to write the constraints all as equality. Since we don't send from this source to that destination, even if I give that value for Xij, it will cost nothing for us. Then all of them are going to be always zeros. So in the dummy column or dummy row, cost coefficients are 0, and the Si or Dj, depending on the type of the dummy row or column, we are going to have the difference between total sum of the supply and demand. There's another question here. It says that the manager or the company's manager wants to know whether it would be desirable to eliminate one of the warehouses. It means that, for example, I have 3 sources, but if I want to eliminate one of them, which one do you suggest, or is it possible or not? First of all, whether it's possible or not, or which one do you suggest? So if you find the optimum solution or the minimum cost, and we check if we make one of these 50 0, it means that even if that supply is not there, we can do this transportation by the same cost, so we don't need that one. We can eliminate that source. Well, this is the one that we can use also the sensitivity analysis. Now we know what is the question here. Now we want to convert this problem, so it's a kind of linear programming problem. I will show how to write the constraints and also objective function. Now, since we have this many decision variables, then we keep variables or these places for the variables. So this is the optimum solution. We will see that if we solve this problem, the mean cost for this transportation is going to be 1,550 euros. If we decide to send 25 tons of that commodity from A to Q and 25 from A to dummy, but since the dummy destination is imaginary, so it's going to have zero cost for us. But still, because we want to write the constraints and equalities and we want to have this 50 equal to 50, then we need to write this 25 there. Now, we select some places to keep the decision variables. So I delete them, so this is just some places we selected to keep the values of the decision variables. What decision variable is this one? This is second row, third column. So here this is x23. If I multiply this x23 means I decided to send this many tons of the commodity or the products from source 2 to destination 3. Since from source 2 to destination 3 we have 50 euro of cost, then 50 times x23 is going to be the cost for this decision. But we want to decide for all of them. So for each decision we need to pay some cost. Then if I multiply allCij's by Xij's and add them up, we can get the Z value. This is going to be the total cost and we want to minimize it. So right now I wrote the equation here. You can see that this is sum product of all the cost coefficients. You can see that you can write the sum product for two rectangular arrays also. I have this cost coefficients and this decision variables. If I multiply the corresponding items and then add them up, it's going to be this one. So I can write one more time. So you can say equal sum product of all cost coefficients, we should select them all, and then multiplied by this decision variables. Now for now it is 0 because decision variables are all zeros. If I give, for example, 1 here for, or 2 maybe, second row, third column. If I give 2 here, then 2 times 50 is going to be 100, the total cost. If I give another 1 here, another 1 times 70, or let's say 3 times 70, 210 by another 100 is going to be 310. So it works. Exactly the formula that we wrote here is multiplying these variables by the corresponding cost coefficients and add them up. Now, for now they are all zeros. How about the conditions or constraints for sources or supplies? Since the problem is balanced and I want to provide all these demands, then I need to send out whatever we have in the sources. It means that if I decide to send x11 from source 1 to destination 1 and also some for destination 2 and so forth, the sum of all these things that we are sending out must be exactly this value, 50. So here you can see that I have a 50. What are these values here? This 50, let me delete them all again and bring them back. So here I have the first source. In the first source I have this much. I can just write equal, click on that. Then since we wrote the rule, I can copy for the others, and you can see that if I click here, it's exactly that 50. So we are bringing correctly. And here also I have this demand. Here I want to bring this demand, and also if I copy this rule for the others, we can see that this is exactly that 25 and so forth. Since on purpose I wrote the demands in column because we want to copy the rule for the columns or columnar. But here also we have some formula. Let's just write one of them and just copy the formula here. The first constraint is for the first supply or the source. So the sum of all these numbers must be exactly 50. It's a basic formula. It's equal to sum of these values must be equal to 50. But since I want the variables or the formula to move down for the other rows, then we don't need to lock the row number or column name. So we move them down. Here I can see that if I click here, it means that this sum must be equal to the right hand side here, correct? Here also similar rule. We want to have this sum or whatever we receive in the first here. These are all products that we receive in the first destination. It should be exactly the one that was as a demand there. So this sum must be equal to 30. Now if I copy this to the others, I get other formula. So this brown cells means there are formulas here. And also xij's are all non-negative. It means that we want to decide to send something from this source to that destination or nothing. So xij's decision variables are all non-negative. Objective function, the type is minimization. We want to minimize the total cost. Now if I click on this objective cell and start to solve the problem by solver, I again start to select from beginning. So the objective is here. The type of the optimization is minimization. Decision variables are all these cells. Okay. And we add the constraints for the rows since they are all the same. These three, not less than, but this time equal to right hand side. And add another one for the demands. For the columns, these sums must be equal to these values. And also we have this non-negativity constraints, and also we are solving with simplex again. That's all. Let's click on the solve, and we have the final solution, which is 1,550 euros for this transportation. But what was the question? The question says, is it desirable? Can we eliminate one of those right hand sides? Let's see. For example, if I don't have this right hand side or this, let's say this source here, if it is 0, let's see what's going to happen to the total cost. If we don't have that, then I don't need this column also. This is also 0, or it's going to be exactly 0 by itself. So if this is 0, that one also is going to be 0. Then I can solve the problem again and see what's going to happen. Now, of course, we may need to eliminate this column, but let's see if it works or not. Now the problem is balanced if I change this one to 0. However, I can change the definition here. Let me change it. For example, for the objective, now we don't need to go up to there. I'm going to continue up to here. And multiply here also. The last one is the dummy, then we don't need the dummy column. This is for the objective. And for this one also, I don't need to continue up to dummy. Then dummy column is not needed. And I need the same for the others. Let me check one more time. Your destinations, that's fine. And here also, this is correct. We don't want to change anything for this, but we don't need the last one. Okay, this is not needed. So we have 3 rows and 3 columns right now. The dummy is not necessary. 1, 2, 3. So let me delete them all. Now this is our problem. One more time. Let's see. Correct. and this one also correct. Now let's solve it again. Now if I solve this problem one more time, but we need to do some change also here. So decision variables are going to be only these 3 columns. Objective is the same place. Let me change the constraints also. Delete them and add again. So one of the constraints is this cells equal that, and the other one is this 3 equal those 3. Okay, and then solve. Now we see that the cost increases. It was 1,550, so increase. So we wanted to have transportation by the same cost, not more. So it's not the case. It's not the one that we will suggest to eliminate A. So now I bring this one back to 50, but make this one 0. I try to eliminate B. So we need to solve one more time. So if we solve, since we updated all these things, we don't need to do anything else. Now I get even more. 2,100 euros is the cost for this case. But if it is there, but we eliminate the last one, in this case, if we solve the problem again, we see that yes, we get the same solution. So this cost, or the total cost, is the same as the minimum value for the original problem. And it says that yes, you don't need the source C, you can eliminate that one. And without that also, you can do this transportation by the same cost. This was the answer for the question here. Now we study another problem. This is also of the same type. Here on purpose I added the dummy row and also dummy column to show that even if we don't need them, then they are going to be all zeros and they will have no effect on the problem. But it's better to delete them. If we don't need them, we can delete the rows and columns and solve the problem. But here on purpose I wrote like this just to show you how it works. So now again we have another problem. We have this cost coefficients in the given matrix form. Then we bring them all here, the same numbers, and again they are sending unit of commodity from source I to destination J. But in this case we should take care, for example here we have from in X, Y, Z we have 22, 15 and 8 tons respectively. These are SIs, we wrote them here. For DJs or for demands we have 7, 12, 17, 8, these blue cells here. And the cost of transporting one, so this is for a ton, okay, for example 2 euros per ton. From the factories in the centers of consumption is indicated in the following table. This is the same. So here also we don't need to do any change because this 8, 15, 12 also are given in tons and the price also given per ton, so we don't need to do any change. But in some case it might be different. For example, it might be given in ton, but some of the information might be written as, for example, 8,000 tons. Then you can factorize with 1,000 and write your objective function 1,000 times the same sum ofCij's. Cij multiplied by Xij's. Now by this information again our problem is unbalanced. This time also we need dummy column. But I want to do some changes and show what did I write in this cells here and there. Here I said that if A10 is greater than B10. In A10 I saved the total supply and B10 total demand. If the supply is greater than the demand, then we need dummy destination, and what we want to give the difference between these two, the total supply minus total demand. Otherwise we are going to write it 0. It means that we don't need this dummy column, so it is 0. Here also the same. This time if B10 is greater than A10, it means that demand is greater than supply, then I need a dummy supply, and for that I need this many, or this number in the SI value. If it is not, or otherwise it is 0. For example, in this case, since the sum of SI's is greater than DJ's, then I have only this value, the other one is 0. But if I change, for example, this value, instead of 8, if I change this to 9, it becomes a balance problem, then both are 0, so we don't need this dummy row or that dummy column. But if this is more than that, for example, if it is 12, if we have 2 or 3 more demands, then I need a 3 here for dummy supply. So this is how to write all these things, as I explained here. Also, in case supply is greater than demand, we need dummy demand, less than we need dummy supply, otherwise we don't need them. We can eliminate this row and that, or that column. So originally this is 8, and the solution is given here. It says that the responsible officer consider this solution for the problem by experience. Now we want to see that whether it's a good solution or not, it's acceptable or not. So I simplify this information in a tableau there. I will remove this question, but we can see that he decided to send from X to 2, from X, this source, to destination 2, how many units? 12 tons. From X to 3, 1, from X to 4, 9 tons, from Y to 3, all 15 will be sent to 3, and from C to 1, 7 tons, it's C by C, it is this is Z, the third one, and from C to 3, 1 ton. Now let's see whether it's going to be a good solution or not. First of all, we solve the problem and find the optimum solution. So this is the part that is given. If I write all the rules as we did in the previous example and solve the problem, we will find the minimum cost to be, or the total cost has minimum of 99 euros by this decision. Okay, if we solve the problem, let me delete them all again and start to solve by all those constraints as we did in the previous example. You know how to write it. Then it says that the total cost is 99. Now we want to check these values, so you can see that by that solution all the constraints must be satisfied. Here we have left hand side 22. Since all the constraints are equality, then we should have left hand side all equal to right hand side. 22, 22, 15, 15, and so forth, all of them. Now, since we have demand of 8 in the fourth destination, then we shouldn't send more than 8. But in the question, or this answer says that we want to send 9 tons for this destination. This is a solution. Let's say whether it satisfies the constraints or not. So I put this data, I copy them and put instead of these values. Now we can see that it satisfies the first constraint, the second one, but not the third one. What's the reason? We will see the reason. And also in the columns we have all the demands, first one, second one, third one, but the fourth one, look, we are sending 9, however the demand was 8. So it's better to send exactly what is the order, the demand in the order, not more. So the answer is a good answer, not bad one, but still it's not with the minimum cost. The minimum cost was 99, but this solution gives us a total cost of 105. So if it satisfies the constraint, so it's feasible, but it is not the optimum solution, since in the optimum solution we had the total cost 99. Now this is how we can solve a transportation problem by simplex method. As I said, it's not the best way. We will solve this another time by two different methods. One's with transportation algorithm directly using a transportation tableau instead of the simplex tableau. And we are going to have some entering, leaving variables based on the dual variables. We are going to find the radius cost and so forth. And also on a network, we will use network simplex algorithm to solve this problem. And there also we will use the dual variables or the duality theory. So for now, we finished by two exercises, just starting with transportation problem and showing that we can solve this problem by simplex method, or we can write the linear programming model for any transportation problem.